Today we will talk about evapotranspiration more, but mostly regarding the Penman method. This one I already showed you in our previous meeting, the original Penman, because this experiments carried out in the UK. So if we want to use it widely, we have to change it, like modify it. And then the FAO already modified the original Penman equation, coming like this. So here we have the constant, the adjustment factor, and then we have the weighting factor, net radiation, another weighting factor, and then wind speed function. And this one is the differences between the saturated vapor pressure, ES is saturated vapor pressure, and then actual vapor pressure, EA. Here, you have to note that in the PDF file that I uploaded, the original file, the original Penman equation, the original modified Penman equation, the equation is not ES minus EA, but EA minus EB. I don't know why it's EA minus EB, but for the EA in the PDF equals to ES in this presentation. I changed it into ES minus EA so that it's more related to the original meaning, because ES is the saturated vapor pressure and EA is the actual vapor pressure. Yeah, it is written as EA and ED. So when they mention ED, it means EA. And then when they mention EA, it means ES. I hope you're not confused with this thing. You just only have to remember if the ED is coming out, and then also they use EA minus ED. First, we will talk about the vapor pressure, the ES minus EA first. So in this presentation, we will talk about all of these variables like ES minus EA, and then FU and W, Rn, and the last one we will talk about C. First, let's talk about the vapor pressure. In the PDF file, in the Penman method that I already uploaded, there is this table. So there are a lot of tables regarding this Penman method. For vapor pressure, the focus is on table 6, table 5, and table 6. Oh, why is my internet connection is unstable? It's 4G. And the differences between the mean saturation water vapor pressure, ES, and the mean actual water vapor pressure, EA. By these ES and EA, we can know from these various data. So usually the data is not known as like the water vapor pressure is blah blah blah. No, usually the data known is the relative humidity data, or the temperature of wet and dry bulb, psychometer reading, or the dew point temperature data. So from these three things, we can know the humidity, and then we can also know the vapor pressure. The water vapor pressure must be expressed in mbar unit. So let's see the table, the related table. The related table, first, table 5. Here we have saturation vapor pressure, which means here is EA, which is actually ES. And depends on the temperature, we will have the different EA or ES. And usually in one area, they have like average temperature, and for the average temperature, they will have different saturation vapor pressure. And then other than saturation vapor pressure, there is this ED, which is EA, the actual vapor pressure. It is related to the temperature data, in dry bulb and wet bulb. It's related to psychometer reading, and here the data is also related to the altitude of the area, the height of the area. Like when the area is in the low elevation of height, and it will be the left one. The data will be in the left one, and then if the area is on the high altitude area, the table will be the right one. So it depends on the area that we want to calculate. For example, if we want to calculate for the area in Indonesia, of course, the altitude is in the left side because it's less than 1,000 meter. And then here, if we have the data of the dry bulb temperature, we can use this table. But if we don't have, we can still use the equation. Like there is this equation regarding the relationship between EA and ES in this equation. Like here, it's for the non-ventilated psychometer, but here is for the aspirated psychometer. It depends on the where the dry bulb temperature is counted. Like depends on the psychometer. But if we didn't use psychometer, we still can calculate it using other method. So for the calculation of vapor pressure, there will be three different methods. The first one is if the data known is the temperature maximum and minimum and the relative humidity maximum and minimum. And then besides this, there's the second method if the data known is the temperature maximum minimum and the psychometer is used. So we know the temperature between dry bulb and wet bulb. And the last method, if we know the temperature maximum and minimum, and then we know the temperature of dew point. Here is the temperature of dew point, TD. To calculate ES and EA, here we have maximum and minimum, but we have to average them so that we have the temperature average. And then for the RH, we have to also average them so that we have RH average. And for some areas, sometimes the relative humidity at night is near to 100%. So the EA can be determined from ES and the temperature minimum, because when the relative humidity is near to 100, the temperature minimum will be equal to temperature of wet bulb. Sorry, this should be the wet bulb, and then equal to the temperature of dew point. And here's the example that they give. in the materials. Like here we have the first, the second, and the third method, so that you don't have to use the table number 6. You can only use the table number 5, and then for the other vapor pressure, you can calculate it from the so we have two vapor pressure, the actual and the saturated. From the saturated, we can calculate the actual by multiply this. So here for the first method, we have the maximum temperature, minimum temperature, and the relative humidity maximum and minimum. And then we average them, become the mean temperature and then mean relative humidity. And after that, we look for the saturated vapor pressure of this mean temperature in table 5. So here we have table 5. Yeah, here we have table 5. So the average temperature is, wait, I forgot. The average temperature is 28.5. So we have to look for the average temperature of 28.5. It's near to 28. It's between 28 and 29. So here we got the 37.8. But you can also do the interpolate this data, because it's 28.5. It should be in the middle of in between 28 and 29, so that the saturated vapor pressure can be interpolated also. And after that, we can also calculate the actual vapor pressure using this equation, because we don't have any other data than this, so that we cannot know the actual vapor pressure using the dry bulb and wet bulb thing, because the data is not available. So we can calculate it using the relative humidity. So relative humidity, the mean relative humidity divided by 100, multiply with the saturated vapor pressure. And then we got this number. Then after that, we can calculate the differences between those two vapor pressure. Then we got here 17.5 MBAR. That's for the first method. The second method can be used if we have the data of temperature and psychometer temperature. Here we have the dry bulb and wet bulb thing, which is we don't have in the previous method. And then after that, we can calculate the average of the temperature, as well as we calculated before, 28.5. And after that, we look for the saturated vapor pressure in table 5. And now we can use the table number 6, because we have this data of dry bulb and wet bulb. And let's look at the table 6. So here we have table 6, and from our data, the altitude is in 0 meter. So we have to focus on this table. And then we have the temperature of the dry bulb. So for all cases, altitude is 0 meter. And here we have the dry bulb of 24 degrees Celsius and wet bulb of 20 degrees Celsius. And then after that, we look for the data in table 6A. And And we got this 20.7 MBAR from table 6A. And then we can calculate the differences between those two vapor pressure. And we got 18.2 MBAR. As you can see here, we got different results because in the same temperature, maybe there will be different vapor pressure because of other effects, such as here we have the relative humidity. Here we have the temperature calculated from the psychometer, so that the vapor pressure calculated is also different. And then the last method, here we have the temperature of dew point. Here we have temperature of dew point of 18 degrees Celsius, and we still have the same temperature maximum of and minimum, and then we average them, and we have 28.5. We still have the same saturated vapor pressure from table 5, and here we have the ED, or the temperature of actual vapor pressure. We can also use table 5 for actual vapor pressure. And here we have the temperature of dew point of 18 degrees Celsius. So from the table, we have the vapor pressure of 20.6 MBAR by using this 18 degrees Celsius as temperature of dew point. So for the third method, we only use the table number 5. For the second method, we use table number 5 and table number 6. And for the first method, we use table number 5 and this equation right here. So that's the differences. It depends on the data that you have. You can use one of the methods from these three, but there is this one method that you cannot use. Here is the example of wrong calculation method. And here we have this temperature maximum and minimum. And then here we have the relative humidity maximum and minimum. And here, the wrong calculation method is when you use this temperature of maximum and minimum separately. So you have to average it first, not in the last. So this one is the wrong method. So they calculate the ES minus EA on Tmax, and then ES minus EA and on Tmin, and then they average them. It's wrong because of the function of the wind that we will use on the next step of calculation only applies to the value of ES minus EA from the result of the calculation using method 1 to 3, which we have to average the temperature and the relative humidity first before we start the calculation. So you have to remember this. If the data that you got is the maximum and minimum data, you have to average it first. But if you already got the average data, you can straight to do the calculation method. You don't have to average it again. And then after vapor pressure, here comes the wind function, Fu. For the Fu, there is this equation. Like here, Fu equals to 0.27 times 1 plus U divided by 100, where U is the wind velocity in kilometer per day at 2 meter height. this is the point that you have to remember at 2-meter height. So if the wind velocity that you have is not at 2-meter height, you have to convert it. And then here comes the correction factor to convert it. This formula is only applies if AS minus EA has unit of M bar and calculated according to the method 1, 2, or 3, not the wrong method. So here we use table number 7. So after we use table number 5 and 6, now we use the table number 7 with wind speed data on a height of 2 meters. When the wind speed data is recorded at an altitude of not equal to 2 meters, correction is necessary. That's why we have here correction factor. If the wind speed data is recorded at an altitude of 0.5, 1, 1.5, 3, 4, 5, 6 meters, you have to multiply it with this correction factor. For example, you got the data of the wind speed at 3-meter height, which is equal to 250 kilometers per day. And then you have to correct it into the wind speed at the 2 meters height. By multiplying this correction factor, here we have for altitude of 3 meters, we have 0.93. So that we have to multiply the 250 kilometer per day with 0.93 as the correction factor. And then we got the U of 232 kilometer per day. And after that, we can use this number in this equation. And so that we will have the number of the wind function Fu equals to 0.27 multiply with 1 plus 232 per 100. And then we will have the right number of wind function. And if you want to like not calculating it, you can see in this table directly. So if you calculated it, it will be more precise because there will be a lot of numbers after the decimals. But here in the table, there will be only 2 numbers after a point. Like here, we have like only 0 point something and something. But if you will calculate it with this equation, you will have more precise number. It's the same, like both of the methods are the same. It depends on the wind that you got. Like here, we got the wind in kilometer per day. For example, we got the number of like 100, 200, like 300 until 900. And then here we have like 0, 10, 20, 30. So this table is only applicable if we have the wind speed of this number. For example, 120, so that we can know 120. Oh, so we have the wind function of 0.59 here. And for example, we got this from the previous one, we got this 232. Because of this table, we can only look for the 230. That's okay. So it's around 0.89. But if you want to calculate using the equation, you can do so, and the results will be not have like much different than the 0.89 here. So there will be more numbers after the decimal. And then after the wind factor, or the wind speed factor. Here we have the weighting factor, dW. So there is this 1 minus W and W, it's the same because 1 minus W is the W here depends on the W that's shown on the table 9. For example, if we want to calculate the W for the region in altitude, here it's the example 95 meters with the maximum temperature of 35 degrees Celsius and minimum temperature of 22 degrees Celsius. Please remember that you have to average it first. Then after you average it, you can look for data in the table. Here we have to average it, and then we got the mean temperature of 28.5 degrees Celsius, and then we can look for the weighting factor in this table. It's the same. If you want to look for 1 minus W, you can look for it in the table 8, and then for the value of the W, you can look at the table 9. So it's the same. It is connected because it's here in 1 minus W is equal to, for example, 0.57, and here we have the W of 0.43. So here 1 minus 0.43 is equal to 0.57. So it is related. Table 9 is connected to the table 8. And from this example, we got the average temperature of 28.5. And here we have the temperature of 28. And then here we have 30. So for the 28.5, it's nearer to 28 than 30, so that we can use the data from this 28 because it will be not have much difference with the desired data. And here we have the altitude of 95 meters. Of course, it's not 0, but it's far to 500, so that we can use the data for the altitude of 0 meters. It's better than we use the data for the altitude of 500. And then if we look for 1 minus W, we look for the table 8. After that, we can know the number of the W based on the results. For example, here we got the number of 1 minus W equals to 0.23, so that we know the W is 1 minus 0.23, which is 0.77. Here we have 1 minus W equals to 0.23, and then the W is from the table 9, or from this equation, we can know directly that W is equal to 0.77. And after the weighting factor, we have here the net radiation. The net radiation is the differences between all incoming and outgoing reflected radiation at the Earth's surface. So here we have the incoming radiation from the sun, and then some of the radiation is reflected and then back to the atmosphere. The Rn can be measured, but data is often not available, so we have to measure it from the data available. Rn can be calculated from solar radiation, duration of the sun exposure, and then temperature and humidity. How to calculate Rn is a little bit complicated, but I think we can do it. Here we have like the table that we use is the table 10. For example, here is the table. This is table 10. And for this table 10, if we want to use this table 10, we have to know the latitude of our region and the month of data that we use. Like we got the data from which month, because it will be different. And here we got the part of the radiation which is reflected back by the earth and the plants, with percentage of like reflected by the water from 5 until 7%, and reflected by the plants or crops from 15 until 25%. It really depends on the month also. That's why we need to use this table to calculate it. The remaining solar radiation is equal to the net short wave radiation, or RNS. And here, RNS, we can use it by using this calculation, like Rn equals to RNS minus RNL, where RNL equal to the differences between the scattered radiation and its energy absorbed in the atmosphere. So the remaining will be the RNS. So the Rn is the radiation coming in. So the net radiation coming in. And we will also use the table 11, 12, 13, 14, and 15 related to this formula. To calculate Rn, because here we have to calculate the Rn, so that we have to know the RNS and RNL. And the RNS is the short wave and the RNL is the long wave. Here we have the solar radiation. To look for the actual radiation, we use table 10. And then after that, after we know the RA, here is the table 10. So this is the actual radiation or extraterrestrial radiation, and with the units of millimeter per day. And then we can correct the RA value using N/N is the ratio of irradiation. Irradiation is the number of the actual sunshine hours in one day, and the big N is given in the table 11. Like here we have the mean daily duration of maximum possible sunshine hours. So in different months, there will be different sunshine hours, of course, especially in the region which has 4 seasons. There will be a lot of differences. As you can see in the table, there's this like until 15 hours per day sunshine hours in the summer, but in the winter there will be like only, for example, 8 hours per day sunshine, or sometimes less because of the climate change. And here we can calculate this RS using this equation, and then we calculate the RNS after we know the RS, and here we have alpha. For most crops usually use 0.25, and we can also use the table number 12 to simplify the calculation so that we don't have to calculate it. There's this there's already results for this equation here. Depends on the N/N. So if N/N is equal to 0.7, the results of this equation is 0.45. It will be different if you use the N/N is which is not on this table. You have to interpolate it, or you can simply use this equation using the number that you have, and then you will get the results. And then after RNS, we calculate RNL. RNL is the function of T, temperature, vapor pressure, and then N per N. As you can see here on the table 13, 14, and 15, you will get the number of the function of T, function of vapor pressure here, and the function of N per N. So based on the temperature, you will get the number of the function of the temperature. And based on the actual vapor pressure, you will get the number of the function of the actual vapor pressure. And then here we have the effect of the ratio of the sunshine hours per day, N per N. And you will get the function of the N per N here. Then after that, you can multiply it like the FT, FEA, and FN per N. And then we got the RNL. Then after that, you can calculate the total net radiation by using the differences between the RNS and RNL. Yeah, there will be a much clearer example in the PDF, I guess. And on the end of the slide, there will be also another example in using this calculation. But yeah, you can use this table based on the data that you have. Here we have the temperature, here we have the vapor pressure, and then here we have the N per N, and then you got this number of the function of T, function of vapor pressure, and function of N per N. Then the last one is the adjustment factor. For this adjustment factor, it is needed because initially the Penman equation was assumed for these following conditions. For example, for the solar radiation medium to high, and then maximum relative humidity medium to high, and then wind speed in the day is equal to plus minus 2 times of the night wind speed. So outside this condition, we will need the adjustment factor so that the number of our calculation will be much more nearer than the actual evapotranspiration that happened in the field. So that we will need this adjustment factor, which is which is shown in the table number 16. For example, here we have the first example is this is the table number 16. So if you have the data of relative humidity, and then you got the number of velocity in the day, wind velocity in the day, and then the ratio between wind velocity in the day and the night. And then here we have the solar radiation. And then after that, you will get the number of adjustment factor here. It's usually near to 1. For example, here we have the relative humidity, humidity maximum of 90%. And then we have the radiation of 12 millimeter per day, and a wind velocity of 3 meters per second in a day, and the ratio of wind velocity in a day and night is equal to 3. And if the data is not found in this table, for example, here we still can find it because it's on the table, like U-day, ratio of U-day and U-night is 3. Here we have U-day per U-night is 3 here. So we have to focus on this table. And then we have the U day of 3 meters per second, velocity of the wind in a day, 3 seconds. And then we have the RH maximum of 90%. Yeah, this one here we have RH maximum of 90%. So here the RS, we have, for example, 12 millimeter per day. So in this table, for RS 12 millimeter per day, RH maximum 90%, and U day divided by unit 3, and U day of 3 meters per second, and then we will have the adjustment factor of 1.28. And after that, we can use this number of C adjustment factor in the previous equation of the evapotranspiration. What about if the data is not found in table? We can interpolate it. For example, here we got the number 2 example of H max of 80%. Here we only have like 60% and 90%. Here we have 80%, so we have to like interpolate it. Yeah, it's rather difficult, but yeah, you have to do it. Or if you want to use like the simpler method, you can use like the nearer one, because this one 80% is near to 90%. Yeah, we can use this table because it will not have like much differences between those two. And for example, here we can also like interpolate it using the for example, U day per unit of 3. Here we got the number of 2.1, which is we don't have here. And we can use like number of U day per unit equal to 2.0, because it's nearer to 2.0 than to 3.0. So yeah, you can interpolate it, or you can also use the number of the data which is closer to the number that you got. Yeah, here's the example that you can do it by yourself. There's also this key answers. By using this example, you can calculate it by yourself, and then you will get this answers here, and then you can check it by yourself whether your calculation is already correct or not. And you can ask me if you have like questions regarding the example of or regarding these key answers of this question. Here, for example, you got the data from a meteorological station located at the latitude of 30° north and altitude of 500 meters, which is obtained in July. This data is related to which table that you have to see. Like if the table is related to the month, you have to look for the month of the data that you have. Oh, it's on July, so you will look for the data which is for the month of July. And here we already got the average air temperature, so you don't have to average it by yourself. And then the relative humidity of 55%, wind speed of 250 km per day. It's already at an altitude of 2 meters, so you don't have to convert it. And then the solar radiation ratio M/N is 83%, and then RH maximum of 60%, UD of 3.2 meter per second, unite 2.1 meter per second. And here you have to calculate the potential evaporation of the reference crop using the Penman modified formula of the FAO method. And here you will see the answers and from which table that you got this answer from. Here we got the answers from table 5, and here we use table 9, table 10. You can do it by yourself, and then you can check it also by yourself if you want, whether you are correct or not. Here I already provide you the key answer so that you know that you understand or not regarding these topics. I think that's all regarding the Penman equation. If you have any question, feel free to do so. Feel free to ask in the class. Here we still have like a little bit of time.